Yeah. Okay, so please welcome Alessandro, which will to give a general outline of AdS3 and CFT4 and AdS3 and CFT2 and integrability. Okay. Yeah, so as Stefano said, it will be something very, very broad, and I apologize because there are certainly experts in the audience. But yeah, I try to maybe keep everybody on board because some bits and pieces might be a little bit unfamiliar. And I prefer to give something a bit broader. So don't hesitate to ask me if you think that is not clear. And on the other hand, maybe for like more detailed discussions, we can also discuss a bit later. So just ask and then we see. I would say that we should try to be very informal. So what I want to talk about is how we can compute some simple observables in AdS3 and in AdS3 CFT2 in particular. And the observables are simple, but they're not necessarily easy to compute. So one thing, if you have the string worldsheet at lowest genus, we can put two insertions here, and we get something that in the cylinder is a freely propagating string, and this thing is supposed to be some 2-point function in the dual CFT. Okay, so that's the 2-point function of two local operators of the CFT.
Sorry, here, what is AdS3? Because you're talking about the string worldsheet.
For the moment, I'm being completely general. Yeah. So this is just in any string theory, you can. This could also be AdS5, for instance. You could ask, okay, compute a 2-point function in the dual theory. That's just some freely propagating string. And what we are computing here is really the spectrum of some string state, just freely propagated. Or you can go on and some more complicated pair of cons topology here. And this is, of course, some 3-point function in the dual CFT. And of course, I could go on and on with 4-point functions and so on. 4-point functions, and I think all of you know, are substantially more interesting than 2- and 3-point functions. They are much richer objects. So you start seeing some dependence on conformal cross ratios. But I think that for the purpose of this talk, I will be focusing on this very simplest example and possibly talk a little bit about 3-point functions as well. And of course, this is part of the story because there are other terms that I could have added. For instance, something where I have two insertions of 2 points, but I have also some non-trivial genus here, and then there are higher and higher genus corrections, and these parts are very difficult, of course, so they will not be in the talk, even if there are some things that can be said by the technique that I will be discussing, but they are substantially harder. So
in this picture, you have in mind inserting the vertex operator.
Yes, yeah, that's what I have in mind. Yeah, and for almost all of the talk, I will be talking about having this problem, which is called the spectral problem, because you're really computing the spectrum of the string or the spectrum of the dilatation operator of the CFT. And this is, of course, the problem that you solve or you teach how to solve in the first course in string theory, where you do the chromosonic string in flat space. Okay. But for most string theories, it's actually a very, very difficult problem when you are in curved space. So let me now just tell you. Before going to AdS3, where I will stay for most of the talk, I just want to say something about another celebrated AdS3 example. Spectral problem. So for AdS5 process 5 strings, or for the dual n equal 4 supersymmetric Mills. It means that computing the spectrum of free strings on AdS5 process 5. And this is the same thing as the dimensions of operators or local operators, to be more precise, in the setup that I'm considering. I have to be more precise, even I would say single trace local operators in an equal 4 superior Mills. And the reason why I want to bring up this example is that from n equal 4 superior Mills, we have an extremely good understanding of what this means. And we know how to do with very good precision and up to a very high number of loops some computations starting from the Lagrangian of n equal 4 superior Mills. And we know that if you start from any state that is non-protected and you expand it, since you're in the planar limit, everything that I talk about is planar, you expand things in the Toft coupling, you would have that order by order, you would have some rational piece of the coefficient and then some transcendent numbers. And typically you would have something that at order Toft coupling to the n is a nth degree of transcendence. So it includes a bunch of zetas and is a very complicated object. And typically, the spectrum is not very degenerate. So there are, apart from the degeneracy that follows trivially from the symmetry group of the theory, which is PSU2, 2/4, typically all the multiplets will have different energies as long as the Toft coupling is generic, as long as you're not in the free theory. So as soon as you have a little bit of interaction, everything gets lifted. So this is the sort of thing that you have. Let me just make a comment here, right here, what I said. Very non-trivial spectrum. It's so non-trivial that if you want to ask, yes.
Theory well defined. I mean, so what is the formulation of AdS5 process 5 that you take? Is Berkovich formulation? Or
I will come to that, but maybe you're anticipating what I will say later. I will be studying it as Green-Schwarz strings in light from gauge. That's the way that I will use to try to attack this problem, and the way that has been used with a great success in AdS5 process 5. But for the point that I just made about the spectrum, you can just think that perturbatively from n equal 4 superior Mills, you get some intuition. And then, of course, you would like to get to finite value of the Toft coupling, but that's much harder. But yeah, it's just to say that we should not expect that this problem is a simple solution. Already from perturbation theory, we see that it's a fairly non-trivial problem. We cannot imagine to find some closed form expression for it. And maybe spoiling a little bit the later part of the talk, there are actually techniques to get the spectrum of these objects at finite value of the Toft coupling. The result can be expressed only numerically, but nonetheless, you can interpolate between zero Toft coupling and very, very large Toft coupling, and you can match the perturbative expansion that comes from n equal 4 superior Mills or that comes from the string of linear sequence. So this is a great story of success in studying the spectrum of theory on a curved background, which is a very non-trivial curved background. It's much less trivial than, let's say, flat space or PP wave or other backgrounds where you can do these calculations typically. Now, the aim of the talk is to consider a little bit of a different background, which is a background of the type AdS3. And then you have to put an S3. And then here you can complete in several ways, even if you restrict yourself to backgrounds that have as much supersymmetry as you want. But for the purpose of this talk, I will just talk about the very simple AdS3 background, which is AdS3 cross S3 cross T4. A couple of other backgrounds that you might be familiar with appear where instead of having T4, here you put a K3. Or there is a slightly more exotic one where you have AdS3 cross S3, and here you have S3 cross S1 It's a bit more exotic because you can tune the two spheres, the radius of the two spheres. And some of the things that I'm going to say will apply, but I don't want to go too much into detail. So AdS3 cross S3 cross T4 as half of the supersymmetry of AdS5 cross S5. AdS5 cross S5 is maximally supersymmetric. It has 32 real supercharges. And AdS3 cross S3 cross T4 has 60 real supercharges. And because of this, it has many parameters. Model. So whereas in AdS5 cross S5 at large n, I only had to worry about the top coupling, here things are a little bit more complicated. So,
can you remind us, this is the background that you get from the new horizon limit of D1, D5, for instance?
That's correct. So you can get it from the near horizon limit of D1, D5, but you can also get it from a near horizon limit of fundamental string and S5, or a combination thereof. And
Well,
that also is reflected in these parameters.
Right? With or without a monomorphism.
Exactly. You can have a, I was just getting to that, but you can have a combination of Ramon background fields and an SNS3 form of B field, H or B. Yeah, so that was my almost very next point, because I just wanted to say before saying that there are a bunch of parameters that have to do with the shape of this torus, and they are maybe not so interesting. So several parameters and the shapes of the core, and I will not be discussing them that much. And then, and yeah, I'm slightly oversimplifying, but one parameter is the strength of the Ramon background fluxes. And another parameter is the strength of the E or H SMS. And to this, I associate a coupling, which is H greater or equal than 0, and H very large. Means that the tension of the string is very large, and I'm basically in a regime where the string is almost point-like and then very close to supergravity. And to this guy, I associate another object. Well, as it can be 0 in principle, K, another parameter K, which instead is quantized. And again, very large K sends me to the supergravity limit. So this means that I can play a little bit with both of them, and I can in particular study the families where I have only one of the two, let's say only H or only K.
Sorry, can you remind me? So the CFT has 20.
Yeah, so let me be a little bit more proper.
So 16 is this one they don't.
Yeah, 16. So as it was correctly pointed out, I was a little bit sloppy there. There are 16 shapes of the torus. There are 4 more parameters.
That's right.
That can be combined into a 3 and the singlet under some SU2. This SU2 has something to do with an SO4 that is on the torus, but it's not that important. And the parameter that I'm talking about here is really related to the singlet. The triplet, the three parameters in the triplet, they have the same effect of this on the spectrum as the one in the singlet, but they also you can mimic basically anything in the triplet by turning on this guy here and changing the shape of the torus. So they are related by something like TSTs on the torus to the original one.
I see. But is there a clear mapping between those continuous parameters and the modular of the string theory background?
Yeah. So this is, I think, so several years ago, there was a paper by Larsen and Martinek on this, and more recently, one by Sachs and Stefanski, where they have especially in mind the effect on this of the closed string spectrum.
I see.
So if you guys are talking about some axions or something that.
Yeah, it's an axiom essentially. Yeah, okay. I wanted to be a bit more qualitative than quantitative, but yeah, so that's the picture. But the main lesson is that unlike AdS3, where you have essentially one parameter to play with, which was the string tension, here you can get string tension from two sources that are very different in spirit. So in particular, if K is equal to 0, all the tension comes from this parameter H, which was the one associated to Ramon background fluxes. And the setup is similar, somewhat similar to AdS5 process 5. Because there is no B field at all in AdS5 process 5.
Sorry, Alessandro, going back to this, what you wrote about, which maybe I missed. So you mentioned there are two super limit. One limit.
There is a one parameter family really. There's a one parameter family of super backgrounds.
But you're saying there's a super limit for the large ASS flux background, and then there's another.
Yeah, you can do a scaling limit, and basically you will have some
finite
remaining parameter, which is the ratio of the two.
Is the dilaton also finite?
Sorry?
So I imagine the two super background will be related, roughly speaking, back to duality in type 2. Is that true?
Yeah, I think that they are. Yes.
But under the S2 transformation, is the resulting dilaton still finite in the AS frame?
So the S duality sort of sends one point to another point, and also, well, of course, it does much more. But what I wanted to say is that if you start from a D1, D5, NS1, or fundamental string and NS5 background, you will just get a supergravity background that has both of them, and the dilaton is constant.
Yeah, I'm familiar with the super background you get from the D1, D5, but you're saying there's a super.
You can do the super construction with the more the richer brain system with basically both types of brain in it.
And so in particular, when you have only an S brain, NS fluxes, right? You have an exact string solution.
I was about to get there, yeah.
Which is a bit peculiar because of the continuous spectrum. So
that's absolutely right. Yeah.
Instead, in the case K, where only Ramon vacuum are switched on, do you still have a continuous spectrum?
As soon as you have the tiniest amount of Ramon flux, there is no continuous spectrum.
So they cannot really be related by a duality, right? I mean, there is one theory of continuous spectrum.
Yeah, they are. I mean, by S duality perhaps, because S duality is very non-perturbative in a sense. So it's.
But it also does bad things to the soft coupling.
Yeah.
You can be recoupling and turn on both types of flux.
Yeah. But what I wanted, I guess that your point was that they look like extremely different theories, right?
No, absolutely, I'm agreeing.
Because with the no Ramon fluxes, then you have all this continuous spectrum.
Yeah, for sure. I just mean you can be at weak coupling, so agreeing that you don't have to
Yes.
think of it as strongly coupled. Having both types of flux. This is also standard in flux compactifications for other purposes.
Yeah, I think that Massimo somewhat anticipated my next point, which was that if H is equal to 0, then the three nonlinear sigma model is described by the Zumino-Witte model, which is a fairly simple conformal field theory, even if it's a Zumino-Witte model for that involves SL2R, so it's a little bit more complicated than your compact group, usual compact group Zumino-Witte model. And this was initially done by Maldacena and Uri. Of course, there's a long story, but I guess a big contribution to understanding that was given by Maldacena and Uri, or more than 20 years ago. But very recently, Massimo contributed to this effort. There has been some new effort to understand in greater detail these models, and I think that one particularly nice result is that using this description with some technical aspects that I can tell you if you're interested, but maybe are not so important. A dual was proposed. First, in a very, very special point at H equals 0, K equal 1, which is really the lowest amount of MS flux that you can have. And very recently, there's been another proposal. Maybe that's the jury might be still out on the very recent one by Eberhard. Which is also H equal to 0, but now K equals 2, 3, all of those. Okay.
Yeah, that I found very hard to digest, actually.
You mean the previous one or the?
No, the one with K larger than 1.
But like this paper from a month ago, or the thing that they did a couple of both of them. Okay. The previous one was harder to digest, I think, but maybe we can discuss later.
No, I mean, I don't understand what does it mean to have a perturbative in the
Yeah.
CFT correspondence. It seems that,
okay, qualitative. But just to be to give you a flavor, so the claim is
sorry, there's also a proposal, just to complete the thing, by the Chicago group for K
That's
less
true.
than 1. Right?
Then, yeah, there is also a proposal for K less than 1. That's a little bit less clear to me what is. I mean, it's not really the usual critical string theory. Yes, right? Something
K less than 1 meaning K equals 0?
No, I think it's a some analytical.
Oh, maybe it's -1, or it can be arbitrarily low. This is the
No,
supersymmetric.
K is above the unitary K limit,
Right.
still, but less than this critical value of K equal to 1. So maybe in order,
I think it's an
in order
analytical
notation
combination
is
in
3
K.
and 1 instead of being 1
Okay,
and
okay,
0.
okay.
Right? I mean, you subtract 2.
Yeah, it's a supersymmetric K.
Yeah.
So before we get maybe too much sidetrack, I just wanted to say that at this point, the claim is that this is precisely the symmetric product orbifold of T4, which is a CFT that was, since the very beginning of the AdS3 correspondence, believed to have something to do with this duality, but it was maybe not entirely clear until recently where exactly in the parameter space it would sit. So this is the claim that the symmetric product orbifold of T4 is precisely dual to one particular choice of the parameter, and it is this choice. And here it's a little bit like we were discussing just a moment ago, it's a little bit less clear, and it could be some symmetric product orbifold, perhaps of Liouville, perhaps of some linear dilaton. The jury, I would say, is maybe still out of that. Now,
Sorry,
yeah.
I should have asked this before. Can you remind us, or me, what there was the NS5 and F1 system, right?
That's right.
Which has two discrete parameters, the number of strings and the number of fibrates.
Yeah.
Yeah.
So I think it's
So
one
forgetting about
fundamental,
like-
string and very large number of NS5.
That's the only situation you want to consider as opposed to the other way around.
Yeah. because I think that the way that the large n limit here is realized, if and correct me if I'm wrong, but the level k is really the number of fundamental strings, whereas the number of NS5 is large. At least in this
Sorry,
case,
it's the other way around, right? K is the
Did I mix it up?
flux, that's the flux
NS5
forces by NS5, right? So K equal to 1 is 1 NS5, right?
sorry, you're right.
How many strings are we talking about? I think we're talking.
A lot of long strings.
A lot of long strings. That's right. It's a lot of long strings and one NS5 per.
Where's the quantum number for the number of long strings? I'm just missing out here because the other
It's
K had to do with Ramon, so we're forgetting about that.
yeah. So it's the n of the large n. So here I'm a G string equal to 0, and in that is the fact that I am yeah, and you're right. It's actually a large number of fundamental strings.
So yeah, the number of fundamental strings is 1 over G string, roughly.
Yeah.
And K is the number of NS5.
Okay, good. Thank you. I wanted to just add one thing to the motivational speech here, which is something we noticed with Joe Palczynski a long time ago. I'm not sure if it went anywhere, but you can, of course, also think of the system as being kind of based on the 5 branes, and think of that as a 5-brane theory at finite density. So it's a higher dimensional theory. Let's say we do have a large number of F1s, and you could even have a small number of NS5. So you don't have to actually be talking about a large N theory as the theory you're talking about, and yet you can control it if you have a large density. So the control of the T expansion and all that stuff comes from having large density alone, which was very intriguing because I don't know, if you try and think of doing this in a lab or something, we're not going to get large NC in real life, but we could maybe excite large charge, you know. And as far as the singularities goes, that has a really nice interpretation in that way of, you know, reframing it, which is, in a condensed matter sense, kind of 2 KF singularities and 2-point functions are expected when you have finite density. So that those things that you all find in the continuum has that kind of interpretation.
What did you mean by loud charge?
Large
Big brain charge or?
No, F1. That's why I was asking.
F1, yeah.
Yeah. So you have this higher, it's five-dimensional theory, right? Which could have just low NC, you know, and yet you're at large density. So a state in that theory. It's just interesting that you can control that without large NC. So.
Well, because there is also the charge associated with one of the U1s, for instance, this is the PP wave when you project into large J, and that is also something.
Yeah, so I will maybe I will get a little bit to that, but maybe I'm not sure how much detail I will give. But there is also, I mean, in a moment, I hope to discuss a little bit more in detail how you get to the spectrum and looking at things like larger charge limit of some solution, a bit similar to PP wave, will play a role there. But just to conclude this overview, I just wanted to say this is two very different setups. This is a bit like AdS5, and I was making this point that the spectrum of AdS5 is complicated, and there is all reason to believe that this spectrum is completely non-degenerate and quite complicated. Whereas here you have actually an enormous amount of degenerate in this particular point when you have the symmetric pro-orbifold. But even when you have any level of the Vesuvius-Wittmann model, the spectrum is actually quite simple. There is this continuum part, which is a bit puzzling maybe, if you think of things like for superior means, you don't expect a continuum there certainly. And on top of the continuum, there is a discrete spectrum, but the energy levels depend, much like in flat space, essentially on the total excitation number of the strings, whereas in principle in AdS5, for instance, they would depend individually in a very complicated way on each type of, on each mode that you excite in some very, very non-trivial way. And the question is whether we can try to understand this whole system as a whole. And there have been a number of attempts to try to understand this, typically starting from this very spatial point of the Vesuvius-Wittmann model. Now, I want to take a little bit of a different route because one very nice insight is that if you look at this classical nonlinear sigma model for AdS3 cross S3 cross T4 with some mixture of Ramon and SNS background fluxes, as a classical two-dimensional field theory, this is an integrable model. Exactly like AdS5 process 5 is an integrable model as a classical integrable, as a classical field theory. And the question is whether you can study this as a quantum integrable model and use this knowledge to basically work out the spectrum exactly as it was done in AdS3 process 5. So this is what I want to tell you about in the remainder of the talk. And the way that I will do this is just to, cutting a bit of corner, maybe give you a feeling for what we want to do. So we have our cylinder, which is the string worldsheet for freely propagating string. This is the time, this is the space. And what we want to say is that here at minus infinity, maybe we excite a little bit the worldsheet, we put some particles effectively. These particles will propagate and they will do something complicated here, they will interact, and I will get something like this. Okay, this is the simplest thing that I can sketch. The problem is that it's extremely difficult for any model, even for the simplest relativistic model that you can think, as long as it's not free, it becomes immediately quite complicated to study these theories in finite mode. Okay. So what you do is that you actually send the radius of this cylinder to infinity, and you get yourself in the situation where you are describing scattering on the plane. And this limit here has to do with, at least initially, considering states that have large arc charge. These are, in some particular charts of the gauges, the arc charge. And you see that here, I already drew a very special type of scattering, because, of course, in general, in scattering, the particle number can do whatever it wants. But here I just drew that 2 goes to 2, and in fact, I even drew that this angle here is the same thing as this angle here, which is basically what you have for elastic scattering. And the reason why I drew this is that since classically this is integral, I hope that the S matrix on the worldsheet, I'm always speaking about the 1+1 dimensional model on the worldsheet, is also integrable. And an integrable S matrix has several features. The most important are the scattering is elastic. In particular, there is no particle production. Macroscopically, I should say. Which means that here, when there are interactions, any sort of mass can happen, but if you go infinitely far away, there is no particle production. And the third thing is that the S matrix factorizes.
Sorry, can I quickly ask about number 2? So it's quite possible I'm misunderstanding the setup a little bit, but there were calculations of, scattering a string against a high energy other string, or which could just
So
be like a.
this is not scattering strings, I'm scattering excitation on the string worldsheet. Yeah. No, I know it's very confusing because
Oh,
it's very different. So this is some two-dimensional quantum field theory, which happens to be to encode the spectrum of the string, but it has nothing to do with the scattering of strings. In fact, the string theory is completely different.
Okay, but you're saying even though it is an interacting theory because it's a nonlinear sigma model, so
Yeah.
it will not. Nonetheless, you say it will not.
Yeah. And we know that some nonlinear sigma models are sometimes integrable, and we know that some two-dimensional quantum field theories are sometimes integrable, right? They are rather the exception, but sometimes.
Is it really nothing to do? I mean, you cannot infer anything about the scattering in space-time from this worldsheet scattering?
Yeah, that would be the very last part of the talk if I have time, but it's much more complicated. So I will just give you a keyword. Studying the form factors of a certain operator for this quantum field theory will have something to do with, for instance, 3-point functions or production of like splitting of strings and scattering of strings. But it's quite a different beast. So now I'm just concerning the S matrix. The last thing that I want to say is that the fact that the S matrix factorizes means that if I have some complicated process with P1, P2, and P3, I can resolve as a sequence of two body scattering events. And actually it turns out that, sorry, let's say the time keeps going up. You see that here I first scatter 2 with 3. There is actually another sequence that I could have drawn. And the fact that these two pictures give you the same result is a consistency condition, which is very famous and very important. It's called the Yang-Baxter equation. But here it just arises as one particular consistency condition on what time. So how do you try? If you have to solve that the string theory is integrable, how do you try to go about to solve to find this S matrix in particular, because we will need it if you want to study the spectrum. You can, of course, do perturbative calculation of the string worldsheet, but that's actually pretty hard already. Basically, anything beyond one loop becomes very, very hard.
Are you saying the classical statement is obvious? Sorry. At the top, you said classically this is integrable.
No, it's not obvious.
Okay.
It's not obvious. It's quite non-trivial, but because there is a lot of machinery for studying nonlinear sigma modeling from a point of view of integrability, there is a criterion which goes under the name of well, the existence of a Lux connection, for people that are familiar with this language, that guarantees integrability.
Oh, okay.
So if you can recast the equations of motion in a certain form, you are guaranteed that it's classically integrable.
And that applies to these examples.
Yeah, yeah.
Thank you.
But you had this before, you mentioned that it's not obvious that it's quantum integrable, right?
The whole
So
thing is
scattering is a quantum process. So
yes. So classically, I mean, if it's not integrable classically, we can go home. I mean, there is no chance, right? It is integrable classically, that you can prove rigorously. Now, and it was done by Cagnazza and Zarembo for this family of mixed flux at the ground. Now, if it's integrable classically, there is a hope that it's integrable at the quantum level, and there is a hope that I can compute the quantum spectrum. And now I want to sketch a little bit how to do this to give you some flavor of the physics that you get. Okay? I won't be able to do much more than that. But the idea now is that I want to study the S matrix that will be the central object. For instance, you could try to study the Hamiltonian, you could try to study other objects, but I really want to focus on the S matrix because it has this nice factorization property, and if I can fix the two-body S matrix, I have everything. And to study the S matrix is very good to go in a gauge where you remove all the spurious degrees of freedom. So you're only scattering stuff that is physical. So what you do is that you study the S matrix like on each. And you fix it. The strategy is to try to fix it symmetry. So let me say something about the symmetries of this theory. The isometries, super isometries are given by PSU1, 1 / 2 plus PSU1, 1 / 2. And then there is a little bit of isometries that come from the T4, but they're not very important. And I told you that there were 16 supercharges. There are 8 from one copy, 8 from another copy. So let's say that in here you have an SL2, so L plus minus 1 and 0. You have an SU2, which is your R charge. 3 plus minus and G3. And then you have 4 supersymmetry generators and 4 you would call them superconformal generators. And in the right, or in the other copy, you have exactly the same thing, only that I will call them always with tildes. 0, tilde, plus minus tilde, 3 tilde, 4 tildes, and 4 tildes. But of course, when you fix light cone gauge, some of these you lose, right? Light cone gauge, only what commutes H light cone, which is L0 plus L0 tilde minus G3 minus G3 tilde survives. And this is really some operator which by construction and by virtue of some BPS bonds, it turns out to be positive semi-definite and is exactly 0 on BPST. So it's a very natural object to consider. And it turns out that it preserves half of the supersymmetries. And it's actually quite easy to see what it preserves because the fact that you have L0 here, there is no chance that it will preserve L plus minus 1, and there is no chance that it will preserve J plus minus, but it can only preserve the cartons, essentially, for the bosonic part. And then some of the supercharges, working out which one sits a little bit more work than I can do on the board. It preserves little h, maybe I should not use little h, so it's large h, not to be confused with h light cone. Maybe I will give this guy a little cut or something. L0 minus J3 and h tilde L0 tilde minus J3 tilde. And then a pair of Q's, which I call QA, a pair of S's, which I call SA, a pair of Q tildes, and a pair of S tildes. So this is all that is preserved by this guy here. Let me give you the algebra that these objects form. So a Q with an S is H, and the Q tilde with an S tilde, you guessed it, is H tilde. And since for unitary representation, actually Q is conjugate to S, you already see that indeed separately these guys are semi-definite. And then something very interesting and very special happens. Because when you compute carefully in light cone gauge, the commutation relation between the Q and the Q tilde, you find that it's actually not 0, but the algebra gets centrally extended. So this C and this C dagger are some charges that have the property that they are actually 0 on all states that are physical, but they are not necessarily 0 on an excitation of the string. The reason is that if I consider a state here, it will be made up of several particles of momentum P1, P2, and P3. So if I think of this guy as some state, each of these as a particle in some Fock space, C can very well annihilate the multi-particle state without having a trivial action on each single piece of these guys. Now, this is very strange from the point of view of, let's say, the CFT, because it's something that couples in the dual CFT, it couples, the left and the right algebras. It's something that was noticed first in this context by Gavana and Danai, that maybe didn't really appreciate all the implication of this. And it's something that also appears in AdS3 and was very famously used by Beiser to basically find the S matrix. The fact that you have these central charges and the fact that these central charges, when acting on a one particle state, well, let's even act on a multi-particle state. They have very special form. Which you see is there only as long as H is there, and is immediately zero if the total momentum of the state is 0 mod 2 pi, which is the level matching condition. So this structure of the algebra makes it extremely constraining and allows you to basically find uniquely the S matrix that has all these symmetries and automatically satisfies the Baxter equation. Another thing that is quite interesting is that this algebra has a shortening condition. Meaning that this superalgebra admits both short and long representations. And it turns out that the excitation of this model are all short representation of the algebra. So they satisfy some relation, which is this one. And now, on another board, let me write some interesting implication of this fact.
Sorry,
Yeah.
what is the anti-commutation of the Q with themselves?
0. Everything that I didn't write is 0.
That's curious. So it's a not positive definite charges, right?
Well,
I mean,
they
so
are
you can-
conjugate to each other. Right? So I didn't really write it, but let me write it here that for a unitary representation, basically that's
Okay.
and similarly for the tildes.
Alessandro, the little h here is different from the h there. What is it?
Little h is exactly the strength of the Ramon-Ramon.
Oh, the same thing.
It's exactly that thing. Yeah.
Okay.
Okay. So let me come from some implication to this because I had that shortening condition. Maybe I quickly rewrite it. H tilde equals C dagger. But actually, maybe instead of having H tilde, let's remember that H light cone was the sum of these two guys. And let's give a name, and the name will be M, the difference of these two guys. The reason why I introduced this M is that you see on a physical state, while H light cone can be any real number, positive perhaps, but M on a physical state has to be quantized because it's just a combination of speeds. So C or Z over 2 on physical state.
When you say shortening condition, does that mean acting on short multiplets, that equation is true?
Yes.
Okay,
Yeah.
It's not part of the algebra generally, but it's true on short multiplets.
It is true for short multiplets, but the particles, the string excitation, all happen to sit in short multiplets.
By themselves, I mean, like the individual ones.
Yeah, by themselves.
Okay.
So basically, what happens? Maybe it's a bit.
I mean, it's okay.
Okay,
Yeah,
okay.
yeah.
Yeah, maybe I should have said something. The thing that I wanted to say is that this H icon is actually the Hamiltonian of the model in light cone gauge. So this object here is nothing else but the energy of a single excitation. So it's basically a dispersion. So by all these considerations, and by working out what this M is, which is quite non-trivial for the mixed flux background, it was done by Bethe and collaborators, you can write for a single particle the dispersion omega of P, which is this very interesting form. This is the formula I wanted to get to. That's, I guess, the last formula that I want to write, and I will maybe make some comments. So this, the dispersion relation, is what for a relativistic theory would be square root of p squared plus m squared. And here you see that you have this piece that looks a little bit like the mass, but it depends on the momentum as long as k is non-zero. Whereas here you have this piece, which is actually a periodic function, and it appears when h is non-zero.
Is this like a Stuckelberg sort of combination?
I don't know. I've not seen this particular thing before. So yeah, maybe you can tell me a bit more later, but I've not seen it, if not in this context, this particular combination. And the last thing that I want to say is that this mu, which is some integer, distinguishes the different type of particles that you have in the theory. Particles that are related to the torus, particles that are related to AdS or to the sphere, and so on. Not terribly important. So in particular, if you have that h is equal to 0, so for the Bethe model, you have particles that move at the speed of light, or rather k over 2 pi is the speed of light of this model, possibly shifted like this. And if k instead is 0, you have a typical lattice dispersion. So this is a dispersion relation that we encounter in lattice models and in unequal force periods.
And sorry, this P is
the momentum of one excitation of the two-dimensional model.
Where now the sigma is no longer identified modulo 2 pi, it's continuous, or
Sigma is still identified modulo 2 pi, and you see that there is some interplay between going from minus pi to pi and shifting mu.
Mhm.
So I don't want maybe so this is more for X, but by using this dispersion and the S matrix, in this particular case, you can reproduce the spectrum of the Bethe model, and you see that this feature of shift modulo 2 pi has precisely to do with the spectral flow.
but P is continuous here.
P is continuous because we are in infinite volume at the moment. I will have, and I don't have time for that, but I will have to go back to finite volume, and I will have to impose some quantization condition for P.
Because I mean, we are on the worksheet, but you said that sigma is identified modulo pi or 2 pi. So you're in finite
No,
volume.
sorry. P is identified modulo pi, modulo 2 pi.
I see.
So
Not sigma.
Not sigma. Sigma is unbounded until the moment in which I will have to impose boundary conditions, and that will give me some quantization condition, which in a simple case is just e to the IPR will be equal to 1. But if you have a non-trivial S matrix, it's something like this, the condition that you get. Pictorially, the idea is that instead of saying that you glue something on a circle and you get the wave function to be well defined, while you do this, if you have several particles, you pick up a phase delay corresponding to the various S matrices that you of the particles that you encounter in the process. This is an oversimplified part of the story.
I have a really dumb question.
Yes.
Momentum is identified log 2 pi.
Yes, the momentum, at least here, is clear that it's periodic. Here is a little bit less clear.
Well, yeah, I'm trying
Yeah.
to understand what that, how that would come about physically.
So it's not entirely obvious a priori. It comes out from requiring that you have the correct number of states, that you reproduce the correct degeneracy of the model that you can know from, for instance, knowing the correct action of symmetry generators and things like that.
So if you have this momentum and
Yeah.
then you increase it, and suddenly that's equivalent to what it was before.
So
Except
this momentum you use essentially to construct an almost free state on some plane wave ansatz.
okay.
So shifting p by 2 pi actually in this ansatz, using the fact that the size of the model is a quantized integer, is a symmetry of that doesn't change your wave function. So shifting the momentum by 2 pi does not change the wave function. That's the correct way to say it. That requires more details than I give, so it's not obvious from what I.
In some sense, one would expect to see that S duality takes you from this H equal to 0 to K equal to 0, no?
Yeah, I don't know how to see that honestly, because this so these are both constructions in the larger limit, where I just look sort of at the spectrum of free strings without considering. So this is just the spectrum of short strings without considering, all the things that you could have on top. So you could have, for instance, windings on the T4 and so on. So you would have to do much more, I think, to see S duality. In principle, I agree, but how to see it, I think even in unequal force pyramids where there is more understanding of the spectrum, I think that's not clear.
But as you said, in the what is it? In the K case, it's always a real written. You have control on what is the sigma model. But do you have any clue how does the sigma model look like for the one case?
Yeah, the sigma model, yeah. So the sigma model in both cases you understand, and the only thing that changes is really how the fluxes are coupled. But what you don't understand is the dual when you are outside of the NSNS case, and you don't know what the other, how to compute any quantum observable. You understand the classical sigma model. That's all you understand.
Sorry, but here when you talk about free strings, it means that implicitly you're working a G string small, right?
Equal to 0. Even,
Equal
yeah.
to 0. So for S duality.
Yeah, exactly. It's not. Yeah, that's what I wanted to say. S duality should do something that.
Because you know that there are. I mean, in the H equal to 0 model, you have long strings that create a continuum, long fundamental strings that create a continuum, right? Because it takes a finite energy for the strings to reach the boundary.
Yeah.
Here, I imagine if you do an S duality, the same role would be played by the T strings. You could have long D strings that reach the boundary, but the G strings small, they are very heavy. So
You would have to understand how things reorganize themselves at different parts of G.
So here you may be missing, or probably you are missing the non-perturbative part of this.
Absolutely, yeah. This is all in the free theory. I don't want to say. I mean, there are other things that one could say, like for instance, how the long strings come out of this dispersion relation and things like that. But I think that is a bit. I would call it exciting. Is that now you have something that really interpolates between these two different regimes, and just to make a statement of where we stand, we understand the representation theory that you can use to construct the S matrix. There is a technical but important fact that the S matrix has an overall prefactor and normalization that you cannot fix just by symmetry arguments. That contains all the non-trivial dynamical structure of the theory, like bound states and so on. And that we don't understand in the intermediate regime so far. We understand it in this regime, we understand it in this regime, but we don't understand it in the intermediate one. Once you understand that prefactor, then there is a machinery. It's a complicated machinery, but there is a machinery which is called the thermodynamic Bethe ansatz, is sort of like this thing, but on steroids. That gives you the spectrum. Then there is a whole story about 3-point functions that I didn't have time to go into, but there is also a machinery, an integrability machinery to compute 3-point functions. It has to do with the study of form factors, as I mentioned. And numerical force superiority has been used to reproduce some results from field theory, and in some cases it works pretty well. It's not completely clear whether it's as powerful and as non-perturbative as the machinery that we have for the spectrum. And for AdS3, very recently, we saw that in principle you can construct this, you can use the same approach or a similar approach for AdS3. The approach is also valid in the intermediate steps in principle, and it passes some consistency checks, which are the check of 3-point functions of BPS operators, which is some very robust objects because it's actually constant over all these parameter space. So yeah, this is the picture that I wanted to give. And I guess the take-home message is that we have a technique that in principle should work for intermediate values of the coupling. It works at the two extremes. And this technique is much more cumbersome, and it requires much more effort, I would say, than the typical Vesuvius-Witten calculation. Is basically the level of complication that you expect for an AdS5 computation. And I think that's unavoidable, essentially. That's just the nature of the theory. And yeah, that's all I wanted to say. Thank you for your time.
Say again what mu was, I'm sorry.
This mu?
Yeah.
So this dispersion relation is valid for several types of particles, and this mu identifies different particles. For instance, the bosons on the torus would have mu equal to 0.
Okay.
Other particles would have mu equal to 1 or 2, and so on.
But when you shift p by 2 pi, you could reabsorb it in a shift of mu, right?
In this case, yes. In this case, no.
But yeah, that's why I was trying to ask about mu. Is it like a flux which is quantized and you can shift it, or it's? But the way you just described it to me is.
No, I don't think it's not that much like a flux. It's really, yeah. So the thing is that in this picture is very clear that this mu is really the mass of the. So that's why it's called mu. It's really a mass for this particle, because at p equals to 0, you really have this. Here it's a bit trickier because you can shift it a little bit. I mean, it's still true that at p equals to 0, the energy is mu.
So sorry, we're on the world sheet. There's a mass for the particle.
Yeah.
And that is coming from
the fact that you're in light gauge, essentially. It's like in TP wave, essentially, right? If you have Ramon flux, then you have a mass for the particle.
Okay, yeah. Ramon flux certainly introduces mass.
And indeed, yeah. So if you take the PP wave limit of this story.
Oh, but the Ramon flux is quantized, so that it is like a flux in that sense. Maybe. Is that
But
right?
that's the H parameter.
Well, that's right, exactly. So that's H. So
I would say that it's quantized just because this object for physical states is quantized. It's a spin of the particle. It's the spin of the excitation on AdS minus the spin on S.
but, sorry, that's a mu.
Yeah, mu. Yeah. So this whole thing is the eigenvalue. This whole thing is the eigenvalue of M, as it turns out. And if you want to map it to something that is physical, you have to study physical particles that have p equal to 0. And then it's literally true that the eigenvalue of M is mu for physical states. Yeah, it's
related to the winding sector. It's related to the winding number.
No, it's something else.
It's not.
You could have winding sectors that would be something else.
0. You say even at H equal to 0, this mu is not related to the winding sectors.
At H equal to 0 is related to the spectral flow.
I thought the spectral flow is how you generate the winding.
It depends what winding you're talking. So there is a winding
In the symmetric orbit.
in the symmetric orbit. Okay, yes,
Okay.
but that's. I mean,
H equal to 0.
yes. I mean, there is also a winding of the strings that has nothing to do with it.
Sure.
But because of that sort of interpretation, the mu is the mass of a given excitation. However, there are excitations obtained by shifting mu by integers. Basically.
Yeah.
Okay. So that's why you could
Yeah.
think
So
about reabsorbing it.
So in this case, it's sort of transparent that mu is the eigenvalue of n. So something that does not have any spin on AdS or on S, like things that are related before, have mu equal to 0, then you can have basically fundamental excitations, like for instance, a boson on AdS3, you would have either mu equals to +1 or -1, and then it turns out that you can construct bound state representation that have larger and larger mu's, or in absolute value. Here is a little bit more complicated because for a particle that is not on shell, then this thing is not even quantized. P could be a real number, and you can use it to interpolate.
Is it not natural here to implement the spin chain formalism and get this? Like
So to interpret
this result?
the spin chain formalism is much more natural, yeah, to be honest. Because this thing is a lattice-like dispersion, and that's what you would expect for a spin chain, I would say.
And this relation here looks like
This one, yes, spin chain, yeah. So this is the Bethe ansatz, and the Bethe ansatz exists both for quantum field theories and spin chains, and it takes more or less the same form. Yeah, so yeah, there is a whole question of what is the spin chain, if there is a spin chain dual for this. Here is more natural than it is here, and I think in both cases it is a difficult question.
Just for curiosity, what is the sigma model? I mean, if you want to write it down.
Sigma model is, I mean,
so okay, there is this
So
free string. You are in Green-Schwarz, right?
in Green-Schwarz, so you can write it in a bunch of ways, for instance, with this methyl cycling action, so it's a superposit. But what it is really a string on AdS3 cross S3 cross T4 with a three-form flux, which is proportional to the volume of AdS3 plus the volume of the.
But I mean, you say that in the light cone gauge, you could do all these things.
Yes.
So how is the action in the light cone gauge? Does it have?
So you take the Green-Schwarz action, you pick as light cone coordinates time in AdS and the great circle on the sphere, right?
But it's in the PP waves, it became a free action. Right?
No, it's not free. It's
In
not
this
free.
is instead.
So if you want, it has an expansioning field whose leading order is the PP wave, but then it has it's basically some. It looks like a non-Bugotto type action. Okay, it has some. If you just look at the bosonic part, it's basically some square root type object where you have the metric of the transverse coordinates appearing in all cases, essentially. It's a pretty unwieldy object, but you can use it, this thing, you can use it to study things like giant magnons and so on. So there are some soliton solutions to this theory, even in light conditions.
And does it help in figuring out what is mu or?
Mu?
Yeah.
Mu is actually, I mean, what it is that it's just an integer that levels a representation. What its physical interpretation is a bit more mysterious, but it's because.
So let me rephrase it. If I want to write a local field in terms of the Green-Schwarz variables on the worldsheet.
Right. Okay. So let me put it this way. You fix your light cone gauge. You have 8 bosons and 8 fermions that remain, and the free, if you truncate to the free action, the oscillators for these 8 bosons and these 8 fermions are the excitations, are the particles of this model. Okay, at least they are some of the particles of this model. What you find is that of these 8 bosons and 8 fermions, 4 bosons and fermions have mu equal to 0. 2 bosons and 2 fermions have mu equals to +1. 2 bosons and 2 fermions have mu equal to -1. And they transform in certain representation of this algebra, which you can construct. Then you also realize that when you construct this matrix, you have to be self-consistent. So if the theory admits for bound states, you have to add them to the model. And it turns out that 2 particles with mu equal to 1 can make a bound state with mu equal to 2. So you have to put it in there, even if it was not any of the original 8+8 modes. And that's how you get all this tower of positive mu and similarly the tower of negative mu. Yeah, so that's yeah.
Is it possible that you could bootstrap or somehow this S matrix in the intermediate regime, or is that not accessible?
Sorry, I should have been more clear. The S matrix, apart from the overall prefactor, is completely known exactly from a symmetry bootstrap argument for any value of k and h. I mean, it has some form, it fits in one page, it's something, okay? The problem is that this prefactor in front, you cannot fix by any linear symmetry because, of course, something commutes and multiplied by scalar factor is still commutes. You can fix it by things like unitarity and crossing symmetry. The thing is that this theory is non-relativistic. The S matrix will not be the difference of the rapidity, so it will depend separately on the momentum of two particles. So for a relativistic theory in two dimension, you can write things in terms of rapidities, and you can write it as a single complex variable. And essentially, you are studying the analytic properties of a complex, a function of one complex variable. Here, you are still studying the analytic properties of a function of two complex variables. In this fairly relatively simple case, this complex variable lives on a torus because this thing is periodic, essentially. You can rewrite this dispersion relation, you can uniformize or remove the square root in terms of Jacobi functions, as it turns out, just because this is periodic object here. And in this case, it's something even more funky, right? This thing is not. So one thing that you want to do to study a complex function like this matrix is first to find a nice Riemann surface on which there are no branch points. So you only have to worry on where are the poles. For something like, for instance, omega equals square root of p squared plus 1, that you can do by introducing some hyperbolic parametrization. Here you can do it by introducing some elliptic parametrization, some Jacobi parametrization. And here is a little bit stranger what you have to do. So because the analytic properties are a bit unusual, it's harder to solve this crossing equation and the unitarity condition and so on. And the other problem is that even if you were to solve it, it's known that there are other solutions. There is no, the solution is not unique. So who's to tell you which one is the correct one? In n equal 4 superior means, this was a very big stumbling block, which was solved by AdS3 and Stadaker. And one way that they could solve this problem is that they had like a 2-loop calculation from the string worldsheet and a 4-loop calculation from the n equal 4 superior mills, and they came up with some object that matched both sides, and they said, okay, it solves the crossing equation, it solves unitarity, it matches at weak coupling, it matches a strong coupling, we are happy. Here, yeah, we don't have any data from the dual CFT. It's much harder. We can only be guided essentially by analyticity, which, you know.
And without that, can you say anything yet? But without that, you can't say anything about the unemployment spectrum.
No, you cannot say anything intelligent because essentially, in order to really know that, so at a very fundamental level, you need the whole thing to solve this equation in order to really get numbers out. That's the most basic statement. The other thing is that these integrable problems actually have some rigidity to them. So even if we are going through this very complicated object, when you have an integrable theory, at the end you manage to encode everything very compactly in some object that in one go takes into account all the nice properties of the theory. And for instance, this is something that is called Y systems of a theory, or quantum spectral curves. You might have heard these words as just catchphrases. And the idea is that they are more or less the only thing that has all the properties. For instance, if I try to construct this guy, but I truncated mu, or I didn't take the correct domain for P, something will have to go wrong at some point. And if you don't have this crucial ingredient of the phase, it's very likely that you will just get it wrong and get to something that is just complete nonsense and will break down and give you just nonsense. But it's hard to see it a priori, what are the good properties to impose. Yeah.
Sorry, can you say again where the string is stretched or not stretched in this background?
So this would be a string that is somewhere in the middle of AdS, and it's so as long as you are not in this case, it's always a confined string, and how much tension it has is given by this parameter h.
Okay, so although you're talking about an S matrix, it's not that you are making it infinitely long along a Poincare slicing or something like that.
So no, I was no, I wouldn't say so.
So this is not, these are not excitations on a long string. Or are they?
No, there. I mean, it's you can think that this really some excitation. So let me put it this way. You have a string that it's an excitation around some BMN string. That maybe that's the thing. So the vacuum of this theory is really something that moves with the speed of light on a great circle and on the time component.
Oh,
And you're sort of exciting around that.
So, sorry, the center of mass of the string is moving on the great circle of the internal sphere. Is that what you?
Yeah, and on AdS.
Okay, and is it rotating or something to be?
Yeah.
To be large in the AdS or?
No, it's not large on AdS. I mean, so you're perturbing around a point like a point like this.
It's a short string.
It's a
It's
short
a short
string.
string. It's a short string. Yes, it's a short string.
Okay.
Yeah.
So these are all, this is also a spectrum of short strings. You don't see.
With one exception. So when you are here, when you are in this dispersion, something particular can happen. You can have that this dispersion relation can be 0 when p is non-zero. So you can put some excitation that has some momentum and not change the energy of the string. And this is the sort of thing that signals a continuum. This never happens here unless, so if mu is equal to 0, something can happen. That these are just the fact that there are flat direction on T4, and also there you have a continuum, but it's like a stupid continuum. Okay? But when mu is, let's say, 1, and you're not talking about T4, this guy is always positive definite. This guy is also always positive definite. You cannot get it to be 0 when h is non-zero. Whereas this guy, you can get it to be 0 with some non-zero momentum. And these are exactly signaling to you that there is some continuum that opens up. And this requires some fine tuning between what k and what mu and what pr is, which is exactly the condition that you are essentially where the continuous representation appear. So yeah, but it comes in a bit of a funky way because you really start from short strings, and then you get the fact that you have a continuum that open up. But
So you're exciting short strings, and at some point you get very close.
Yeah,
to the
it gets very. You don't pay any energy basically to excite them a little bit more. That's what happens. But you're exciting short strings, yes.
And now supergravity gives you a lot of data also on the 3-point function, etc.
Yes.
So I suppose that you have already
incorporated
them as a
yes.
check.
Yeah, for the 3-point functions, yeah.
Does that only allow you to fix this prefactor partially, or?
No, I mean the problem of like the supergravity modes are actually a very small part of the spectrum, and it's a part that is very robust, which also means that it's not very sensitive to all the parameters of the theory. So it's not enough to really give you the information that you need, unfortunately. Okay.